Okay, so lesson 3, factoring the greatest common factor. Now we've looked at greatest common factor before, but previously when we looked at greatest common factor, we were just looking at the greatest common factor of two known numbers. Now we're going to look at the greatest common factor of polynomials. So to start, let's just do a quick review of how to expand polynomials. So 2x times 3x plus 1. So we'll do 2x times 3x is 6x squared. 2x times 1 is just 2x. That's our expanded form. Pretty simple. Today our goal, though, is to go the other direction. How do you go from this to that? So that's going to be factoring. Factoring is going to be pretty much the most important thing we do in Math 10C. So let's do a quick review of GCF. For numbers, we just use the greatest number that divides two or more numbers without a remainder. So, for example, with 4 and 8, 4 has factors 1, 2, and 4, and 8 has factors 1, 2, 4, and 8. So the largest common factor they have is 4. So the GCF of 4 and 8 is 4. Simple enough. But let's talk about the GCF of polynomials. So for polynomials, the GCF is the largest polynomial that divides into every term of the polynomial without a remainder. It consists of the GCF of the coefficients and the lowest power of any variable that is in all terms. So what that really means is, let's take a look at this one. We've got three terms, 2x cubed, 4x squared, and negative 8x. Those are our three terms. So we want to look at what's common between those three. Well, first off, the GCF of 2, 4, and 8 is 2. That's the GCF of our coefficients. Then we look at x cubed, x squared, and x. What's the largest number of x's they have in common? Well, they all have at least one x, and 8x has only one x, so that's all they have in common. So ultimately, the GCF of this polynomial is 2x. In general, don't worry about the negative signs when looking for the GCF. We'll talk a little bit more about that in the future, and there will be a case where it will kind of matter, but for our purposes right now, don't worry about the sign. It won't affect your GCF. Your GCF for now should just be positive. All right, let's take a look at an example. So consider the two polynomials, two monomials in this case. So we want to figure out what the GCF of these two things is. So what I'm going to do is I'm actually going to prime factorize the coefficients and break down the exponents, the variables, to show you what I mean. So first off, 18 prime factorizes as 2 times 3 times 3. That's just the prime factorization of 18. Then I have 1x and 2y's. Okay, 27 is 3 times 3 times 3. It has 3 x's and 2y's. So we can see there are 2 common 3's, 1 common x, and 2 common y's. So the GCF is 3 times 3 times x times y, or 9xy squared. That's our GCF. So if you ever have a really hard time figuring out the GCF just by looking at it, you could always go ahead and break it down like that and find all the common pieces that way. All right, so we're going to find the GCF of these three different sets of polynomials. All right, so let's start with 14x squared y and 28xy. So 14 and 28, they share a GCF of 14. X squared and x have an x in common, and y obviously have a y in common, so that's their GCF. Then we have 12a squared b and 8ab squared, so the GCF of 12 and 8 is 4, the GCF of a squared and a is a, and the GCF of b and b squared is b. So we've got 4ab. Again, if you do have a hard time just seeing it right away, you can always prime factorize it, right? 12ab squared, a squared b, sorry. This is the same as saying, okay, this is 2 times 3 times a times b, while 8ab squared is the same thing as 2 times 2 times 2, A, B, B. And you can see that they have the 2's in common, 1 A in common, and 1 B in common. All right. Then we have 3. Now again, don't worry about the negative. It's not going to be a big deal for us right now. We just have to look at the numbers. So 5, 15, and 10 all have a 5 in common. X squared, x cubed, and x to the power of 4 have x squared in common. Y squared, and y have a y in common. So it's 5x squared y. Okay, so now we're going to learn how to use factoring to help us break down polynomials into pieces. So later on, when you guys are doing Math 20, you're going to be using factoring in order to solve problems. For now, we just got to teach you that skill. How do we break a polynomial into chunks, into smaller and smaller pieces? So in order to do that, to factor or rewrite as a product of polynomials, we're going to use the GCF. So 5a and 10 have a 5 in common. That's it. So what we do then is we say, well, 5 times something is going to give me 5a. Well, obviously a. 5 times a would give me 5a. And 5 times something is going to give me that negative 10, which of course is negative 2. So we have that 5a minus 10 is the same thing as 5 times a minus 2. All right, then let's look at the second one. So I have 2x squared and 4x. The GCF of that is 2x. So again, we ask 2x times something gives me 2x squared. That's x. 2x times something is 4x. That's 2. So we can rewrite 2x squared plus 4x as 2x times x plus 2. Now here's the cool part about factoring. If you don't know if you did it correctly, all you have to do is expand it. 5 times a is 5a. 5 times negative 2 is negative 10. If you get back to the original polynomial, you know you did it correctly. Now let's start looking at some, without that sort of breakdown for us there, where we're doing it all on our own. I'm going to show you a slightly different way you can think of it if you have a hard time figuring out what's left over when you take out the GCF. So factoring, another way of thinking of factoring is that you're dividing every term by the GCF and then multiplying the whole polynomial by the GCF. Because if you both multiply and divide by the same thing, they cancel each other out and you haven't changed the polynomial. So 9ab and 12ac, well, their GCF is 3a. They have a 3 in common, they have an a in common. So to figure out what goes in the brackets, what we can do is just say, hey, to get that 3a out of there, we basically divided everything by 3a. So this is 9ab over 3a minus 12ac over 3a. So we have 3a times 9 divided by 3 is 3. The a's cancel out, and we're left with the b, 3b. Negative 12 divided by 3 is negative 4. Again, the a's cancel out, and we're left with c. 3a times 3b minus 4c. And again, to check your work, you just expand it and see if you get back to here. All right, let's try D. So in this case, my GCF, I've got a 2 in common, I've got an x in common. What's left? Well, we got 2x cubed divided by 2x, 4x squared divided by 2x, and 8x divided by 2x. So we see the 2's cancel here, and x cubed divided by x is x squared. 4 divided by 2 is 2. X squared divided by x is x. 8 divided by 2 is 4, so minus 4, and the x's cancel, so that's all. Ooh, I used a big one that time. Let's use a little one. There we go. So that is our factored form. Well, that's our GCF factor out anyway. We'll learn how to factor this further later on. All right, next one. Common is 5. We also have an x in common. 15x squared divided by 5x. Negative 10xy divided by 5x. negative 20xz divided by 5x, and we get the 5x left out front, 3x minus 2, the x's cancel and we're left with just the y, minus 4, the x's cancel and we're left with just the z. All right, let's get to one that's a little bit trickier. It's got something a little bit trickier in it. 7, 14, and 7. 7, they all have one a in common, and they all have at least two b's. So, what's left? Well, we have the 7a cubed, b cubed, all over 7ab squared. We have the 14a squared, b squared, all over 7ab squared. And we have the 7ab squared, the negative 7ab squared, over 7ab squared. So what does that give us? Well, here the 7's cancel, and we're left with a, b. Then 14 divided by 7 is 2. 1a left. Both of the b's cancel out, so that's gone. And finally, well, 7 divided by 7, that's 1. A divided by a, that's 1. And b squared divided by b squared, that's 1. They all cancel. Now be very careful. It is common for students to cancel everything and say, oh, that's it. We're done. The term is closed. There is just no final term. But that's not the case. When we cancel by division, the result is 1. 7ab squared divided by 7ab squared, any number divided by itself is always 1. That 1 is super important. Because think about it. 7ab squared times the ab, that gives me this term. 7ab squared times the 2a, that gives me this term. 7ab squared times the negative 1 gives me that term. If we didn't have the negative 1, this term wouldn't exist. And then the polynomials wouldn't be the same. And they have to still be the same. So we have to not forget about that 1. All right, on this next one, I'm going to skip the division step. So I'm just going to do the division in my head. So first off, GCF of 5, they all have at least one a in common, they all have two b's in common, and they all have two c's in common. Okay, 45 divided by 5 is 9, a squared divided by a is a, b cubed divided by b squared is b, and c to the 5 divided by c squared is c cubed. Minus 15 divided by 5 is minus 3, a cubed divided by a is a squared, b squared divided by b squared, those cancel, c to the 4 divided by c squared is c squared. Okay, here's the fun one. 5 divided by 5 cancels. A divided by a, cancel. B squared divided by b squared, cancel. C squared divided by c squared, cancel. But we don't stop it there. We can't. This and this are the same. That means we're still having that 1 there. So that when I multiply everything back, I still get this term. Otherwise, I would only have a 2-term polynomial. And I need 3. Okay, finally. 2 pi r squared plus 2 pi r h. This might look familiar. This is the surface area formula. In case you thought that looked familiar, I'm going to show you a way to do the surface area formula actually a little bit faster. By factoring, you can actually put less into your calculator. So there's a 2 common, and there's pi common, and there's an r common in each of these. Bracket. Well, if I take out 2 pi r from 2 pi r squared, I'm just left with 1 r. If I take 2 pi r out of 2 pi r h, I'm left with just an h. So if you're ever looking for a less numbers to type in version of the formula for surface area, this one works. Okay, now we're going to learn how to factor polynomials out of other polynomials. So, for example, if you look at this guy right here, you can see that there are polynomials inside each term. There are little binomials inside the term of this polynomial. The trick to this one is finding what's common. So you'll notice x minus 3, x minus 3. It's in both terms. So then I look and I pull out an x minus 3. That's the first thing I want to do. Then I say, okay, what's left over here? Well, 7x and positive 4. Don't drop the sign. Really important, we keep the sign there. So we're left with 7x plus 4. That is factored form. And if you want to make sure that you did it right, well, oops, too small. You can check using our distributive law. We can multiply the entirety of x minus 3 times 7x, and then the entirety of it by 4. And you'll see x minus 3 times 7x is 7x, there we go, times x minus 3. And then x minus 3 times 4 is 4x minus 3. Woohoo! It's the same. All right, let's try this one. So you can look at what's common. Our blue is a plus 9. We have an a plus 9 in each of these. So I start and say, okay, I'll pull out an a plus 9. I'll factor out an a plus 9. Then I say, what's left? I have a 2a and a minus 3. So what's left is 2a minus 3. This is just the reverse of that distributive law that we learned back when we were doing polynomial expansion. It's just going backwards. We're pulling out the a plus 9 instead of distributing it in. Finally, this one looks a little bit different, but it's really not. We have x plus 5 and x plus 5. So we pull out that. Then we look at what's left. It doesn't matter that they're right next to each other. Still, what's left is 3x minus 7. So that is how you factor a binomial from a polynomial. It actually works with any polynomial. It could be more than two terms, but the reason that we show you this one is this is actually an intermediate step on something we're going to be doing on Friday. And so learning this now just kind of helps prepare us for that lesson later on. Okay, one more type of factoring that we're going to look at in this lesson is going to be factoring by grouping. Sometimes you're going to see 4 terms in a polynomial, and there will be no common factor between all 4 terms. So a trick that we can sometimes do is look for groups. So, for example, here, well, if I don't have anything common between all 4 of these. There's nothing common between 2, 6, 5, and 15. There's nothing common in the variables. But there are commonalities in these two, and there are common things in these two. So I'm going to do them separately. So first, I have 2ac and 6ab. I'm just going to factor those two. So they have a common factor of 2, and they each have an a, and that's it. So I see what is left. So I pull out the 2a from each of those, and I'm left with a c, and I'm left with 3b. Then I'm going to look at my second set. Well, they each have a 5 in common, and they each have a b. And then I see what's left. Well, there is a c, and 15 divided by 5b is 15b squared divided by 5b is 3b. So that was my 2 pieces in my grouping. But now that we've done the factoring by grouping, this should look very familiar. Now we have that c plus 3b that's common between both sets. And then we look at what's left over, 2a plus 5b. Boom. And of course, you can check your work by expanding. B, similar idea. Now, you don't always have to pick the pairs that are right next to each other. Just so happens it's conveniently set up like that right now, but we don't have to. We could do it other ways. We could rearrange them. For example, I could rearrange this one to be a squared, and I could move this guy over and make this a squared plus ay plus ax plus xy. I could do that. I still have groups that have things in common. You just want to make sure, however you organize them, the pairs are in groups where you can find something common. So a squared and a, they have an a in common, and that leaves me with a plus y. Ax and xy have x in common, and that leaves me with a plus y. So now I have my common a plus y in each of these. And I have what's left over, a and positive x. And there we go, fully factored. 2 more to go. All right, let's look at this one. 6m squared times n, 12m n squared, 2n plus m. Okay, so there's something I could right away, if I wanted to, factor some things that are common between all of them. They all, well, actually, no, I don't have anything in common. I still don't have anything in common. What am I talking about? They don't have anything in common. Puh. We got a group. So I'm going to look at this group, and I'm going to look at this group. So first group, 6m squared n, 12m n squared. They each have a 6 in common, an m in common, and an n in common. When I factor that out, I got 1m left over and 2n. The second one, now, there's nothing common between 2n and n. That's it. There's just nothing I can do. So if there's no common factor, remember, that means they have a GCF of 1. Now you might say, oh, but these two aren't the same. Well, aren't they though? 2n plus m and m plus 2n are the same thing. So I can just rewrite this. Now, you don't have to write this one, but don't forget, when you're factoring, you definitely need to account for it. Because, oopsie, wrong line. Here we go. Here's our common factor. If we didn't write the 1, we'd need to just remember that it's there. We need to just know that it does exist, because we definitely don't want to not have the plus 1 in our answer here. And that's factored form. Oh, and hey, we've done this one already. I accidentally wrote the same question twice. Whoops. Repeat. So we don't have to do that one. And that is the end of the lesson.